to speak about classification methods. In classification methods, we are dealing with trying to find a relationship between a bunch of quantitative variables or qualitative variables to some qualitative variables. So our output is always categories. Our inputs can be in terms of categories or quantitative variables. So our main assumption here, which make a distinction between what we have today and what we had yesterday, is qualitative outcomes, categorical outcomes. For instance, let's say you want to use the information of genome to decide and predict eye color. Eye color can only get 3 values in our data set: blue, green, and brown. So if you want to see how different genes will affect this color, you have to use some type of classification method, because our outputs, which were eye colors, are classification. Or another classical example, if you want to look at the keywords you have in your email and see whether it's spam or ham. Ham is the opposite of spam. You also use a classification methodology. So to formulate what we said earlier in more mathy version, we say we have X variables, X predictors, and we want to use these predictors, which could be both qualitative and quantitative. It doesn't matter actually. We want to find a function of them and relate it to an output, and here our output is definitely a categorical variable. We're going to find the best classification function that describes that. So usually, not only are we interested to know what class does these inputs signify, but also want to see the probabilities of it. For example, we want to see what is based on these keywords, what is the probability of, let's say, spam email, or what is the probability of ham email. Let's say if it is 99% spam, it's way more likely to put it in junk mail than the cases that is only 51% spam. Although 51% spam is more likely to be spam, but 99% is so much more likely. So sometimes we're interested to know the percentage of outcomes and probabilities as well. Or for instance, when IRS wants to go after people and audit them, if we go after the most probable fraudulent tax filers, so let's say one person has 99.99% to have fraudulent outcome, and one person has 51%, they would definitely go after 99.99% because they don't have enough resources to go after every single one of their suspicions. So in theory, we are interested to separate the outcomes, and here is an example. Look at this picture, look at this graph. In this graph, we have income and balance, and we have two categories. Our categories are default and no default. These orangish points here are those who defaulted, and this bluish one are those who didn't default. And as you can see, it is dependent on balance and income. So this variable is income, the y variable is income, the x variable is balance. One thing that is pretty apparent is that there is a clear distinction on balance between those who didn't default and those who did. And if you look at the scatter plot, the box plots of these two outcomes, we can easily see that if we just look at balance, there is a clear cut between those who didn't default and who did. Usually, if your balance is around, let's say, 1800, you're more likely to default, and if your balance is less than 1000, let's say around 800, you're less likely to default. And if we look at the income level, we see there is not that much significant effect for income. So it sounds like balance is more significant in this case. So let's see how we can just do what we visually observed in mathematical formulations. So if you have two categories, like before, you're going to assign it to a dummy variable which gets value 0 if one of the cases happen, one otherwise. So for example, here we assign 0 to no default and 1 to default. So one of the things that I usually hear when I teach this course is that, okay, so if we can assign y to 0 if no and 1 when it's yes, we can simply write a simple regression line, write this, y is equal to beta 0, beta 1, let's say balance, plus beta 2 income. And whenever y hat is more than 50% or 0.5, we say it is the probability of default, otherwise we say it's not. So that is one of the first solution comes to mind. Though it may make sense at the beginning, we will see that it's a very stupid assumption to make. And actually, even when I was just studying these topics, the first question I asked myself was, what if I just run a simple linear regression line and assign probabilities less than 50%, cases that y hat is less than 50% to 0 and more than that to 1. As we will see later, this is not a good assumption because we will see that in some of the cases in some linear regression lines, you're always below 0.5 or you're always above 0.5. So that makes all your prediction to be 0 or 1. Sometimes you get probabilities less than 0. And as you know, finding a probability less than 0 is so bad. It's actually, I only see that in my very low-level courses. Some people find less than 0% probability or more than 100%. So if we just use this linear regression line, we may get these functions, these nonsense numbers. The base of this linear regression line can be found in linear discriminant analysis. It uses somehow the same type of classifier with some adjustments, but usually that's not a perfect thing to do. So let's look at the ramifications of that and see what will happen. In left-hand side graph, what you see here is bunch of observations. So here we have balance, and these are the instances that we didn't see default. Here we have again, for balance, we see for these balances we saw default. So if you just consider these many observations and run a regression line, you get this blue line. And as you can see, for very low level of balance, less than 500, you get negative probability of default. Even for the highest level of balance you observe, which was around 3,000, the probability of default is again less than 40%. So if you use this model, what you will expect is predicting no default for everyone, which doesn't make sense. We see a clear cut here. We see that when we surpass 1,500, the probability of default surpasses no default. One of the ways to work with that is use another functional form. We use a functional form that is highly nonlinear and highly flexible, which starts from 0, goes up to 1, or starts from 1, goes to 0. These functional forms, there are many, actually, there's not just one way of defining this functional form, there are many. One of them is logistic regression lines. Logistic functions. We have probit as well. We can make some modification in Tobit models. There are a lot of ways to make sure your probabilities always stick between 0 and 1. One of them is logistic regression lines that we are going to discuss in a bit. Before I go there, we can go even further and have an output that has more than one variable. For instance, you would like to see what are how you can assign different symptoms to different classes of disease. Let's say we want to predict if that this is is a stroke, drug overdose, or epileptic seizure. And let's say you just want to look at it based on the symptoms you observe. So here we have 3 outcomes, and again, we can use some modifications on logistic regression models to work on it. So let's get back to logistic regression models and see how we work on it. Logistic regression line is a function that is always between 0 and 1. That is always between 0 and 1. It is never equal to 0. It's never equal to 1. It converges to 0 and 1. And that has this functional form. One thing I want you to remember is that assume this beta 1 and x1s are vectors. So in other words, we want to have a logistic regression line on 4 variables. It would look like this: exponential of beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 divided by 1 plus exponential of the same thing, beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x2 3 plus beta 4 x4. So this is a logistic function. This is a logistic function. Usually you use L to represent it, so let me use L. L of x1, x2, and x3 and x4. And L is always between 0 and 1. So that's why we define it as probability of belongingness of this these outputs to categories. So if your prediction, if your L hat is less than 50%, you assign it to 0 category. If L hat is more than 50%, you assign it to category 1. You can arbitrarily choose equality in either of these points. So let's get back to our slide. So these logistic regressions, which are extremely powerful, have exponential inside them. They're always between 0 and 1, and they use exponential function. And exponential functions, for those who might have forgot, are nothing but the number which is 2.7182. So e to the power of beta 0 is 2.71 to the power of that. So that's a number like pi. It doesn't have any end. That's a rational number. That is a real number. And actually, the way e was, that's some just side note. I don't want you to remember that, but e is actually 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial till infinity. So if you add these numbers up, what you get is 2.7182. Okay. So these x's are predictors. Px is the probability that it belongs to category 1. So, okay. Okay. One of the great characteristics of logistic functions is that the logarithm, and this is natural logarithm, by the way. Log in this textbook is ln in your calculators. It's logarithm in E. So log of this px divided by 1 minus px is beta 0 plus beta 1x. And px divided by 1 minus px is called log odd. It's called odds. So basically, log odds is a linear function of our predictors. So it has that beautiful linear shape that we were looking after. So let me explain some time on defining odds. Let's say you are a person who may default 80% with 80% chance and 20% no default. So let's see what we get. So 80% was our px, and 1 minus px was 20%. So 80% divided by 20% is 4. So your odds of default is 4 to 1. That means you're more likely to default. If your odds are 1 to 5, or you have a ratio that is less than 1, then that means you are more likely not to default. So that's how odds are defined. So that's why px divided by 1 minus px was defined as odds. So log odds was a linear function of our predictors, and whenever we have linearity, we are cool. We really love it. So a great thing about this logistic function is that it always stays between 0 and 1. It never touches, it never ever touches 0 and never touches 1. It's always between the two. Unfortunately, there is not any closed form solution for finding beta 0 and beta 1 based on our predictors, unfortunately. But fortunately, you can use maximum likelihood and you can numerically solve it. That is slightly above the level of our course, but for those who have more advanced backgrounds, the way you can estimate beta zeros, beta 1 through beta k, are the coefficients of our predictors, is through maximum likelihood method. And actually, maximum likelihood method, in my opinion, is the most powerful method out, because you can use it for any application. So let's say we ran our logistic regression model. So let me write it: logistic of balance. And here are the coefficients we get. We get beta 0 equal to -10, and beta 1 equal to 0.0055. So let me spend some time to explain what are the coefficients of logistic regression lines, how you can interpret them. So our topic is how to interpret logistic regression, logistics regression coefficients. Okay, so to remind you, logistic regression function would look like exponential of beta 0 plus beta 1 x1 plus beta 2 x2 divided by 1 plus exponential of beta 0 plus beta 1 x1 plus beta 2 x2. Let's assume beta 1 was estimated as 1 and beta 2 was estimated as 0.5. So that would mean, in order to interpret beta 1, you should do the following. You should first put it in exponential. So exponential of beta, you estimate this part. Exponential beta 1 -1. That will be e to the power of 1 minus 1. This is always 1, and this is what you have for beta 1. So that is 2.71 minus 1. That is 1.71. So here, what it means is the percentage, the change in odds for a unit change in x1 is 171%. 171%. So you basically, in order to interpret that, you just put it in the power of exponential, take one value out of it, and that number you get would give you the percentage change in odds for a unit change of your dependent variable. Let's say let's do the same thing for x2. For x2, beta 2 was 0.5, so exponential of 0.5 minus 1 is, let me run it on Excel. Exponential of 0.15 negative, okay, negative 1. Oops. Oh, instead of exponential, I wrote WZP. Exponential of that is 0.64. So that means a unit change in x2 will change odds by 64%. 64%. So let's get back to this value and see what that means. So we get balance 0.0055. So let's put it in our Excel file. Exponential of 0.0055 negative 1 is 0.0055. That means a dollar change in balance will change the odds of default by 0.5%. So again, that exponential of 0.0055 minus 1 was 0.0055. That means a dollar change in balance will result in 0.55% change in the odds of default. So let's estimate, so based on these numbers, for this intercept and this balance, let's estimate what are the odds of default at $1,000 balance. So beta hat 0 was negative 10.65. Beta hat 1 was 0.0055. So the only thing that is left is that we replace 1,000 here by x here and here. So if you just plug in numbers, you get 0.006. That means you estimate that on average, the odds of default for $1,000 balance is 0.6%. How about $2,000? For $2,000, we do the same thing, but instead of 1,000, we replace it by $2,000. And what you get is 0.586. That means the odds of default, if you have balance of 2,000, is around 58.6%. Now let's look at the same data set, and we use student as a dummy variable. So you want to find probability of default based on a dummy variable which is a logistic function on studentship. And this is 1 whenever you are a student, that is 0 when you're not. So this is the result you get, is 0.404 for that dummy variable. So let's do our magical math. So exponential of 0.4049 minus 1 is exponential of 0.4049 negative 1 is 49.9. So it's 49.9. So that means on average, students have 49.9% more chance of default. So around 50%. So being a student in comparison of non-students results in 50% more chance of default. And so let's see why we get that number. Let's see why we get that number. So if you're a student, your dummy variable is 1, so you get 43.1, right? So that is the probability of default for a student is 4.3%. If you're no student, you put 0 as dummy variable. So the probability of default would be 29 by 2.92%. And as you can see, 4.3% is around 50% more than 2.92. So the probability, the odds of default for students, 50% more than non-students. Now here, not only we consider students as a dummy variable, but also we consider their income and their balance. So we just run our regression model once again. These are the coefficients we get, and let's compare it with the previous coefficient that we got. Here, the coefficient for students was positive, is 0.404, 0.4049. Here it's negative 0.64. What does it mean? What does it signify? When we included balance and income, things changed dramatically. Why? First of all, we first look at the p-values, and what we can see is that income is not that much of a deal. So we can just exclude that. And if you exclude that, you get almost the same results here in this case. So what is the point? Here we estimate that students are less likely to default. Here we estimate that they're more likely to default in the previous case. What's the point? Where this distinction came from? The answer is we should be very careful when we interpret these results. So let's see what this number signifies. So let's first estimate this part. Exponential of negative 0.64 minus 1. So exponential of negative 0.6468 minus 1 is negative 47. 47. It was 0.67. Okay. It was negative 0.47. That means, on average, you estimate for a fixed level of balance, students tend to default 47% less than non-students. So for the same level of balance, you expect that students default 47% less than non-students. So what is the problem? The problem is, if you just look at the default rate and credit card balance, the first thing you observe is that students tend to have less credit card balance. So for each level of balance, students default less than non-students. So that is the problem. So usually students have higher balance because they have more loan. So students tend to have higher balances because they have more loan, right? So the marginal default rate is higher than non-students because they hold higher balances. But if you just compare apples with apples, fixing all balances for the same person who holds $2,000 balance, students tend to default less than non-students. So we should be very, very careful when we interpret the results. Here in this case, when you have incorporated balance into the equations, and since balance and studentship have very high correlation, we say for fixed value of balance, the students are 47% less likely to default. But being a student means holding more balances, and that is why students, on average, in the previous case, have around 40-something% more chance to default. So we should be very careful when we interpret this data. The next case is looking at a South African city and looking at the data on 160 cases of heart disease. And in this particular region in South Africa, a large percentage of people suffer from heart attack, 5.1%. Why? Because they eat a lot of beef. As you can see in the next slide, a lot of variables such as blood pressure, tobacco use, lower density cholesterol, family history, obesity, alcohol consumption, and age was considered. And here the red things we see here, the red dots, are signifying heart attack. The blue ones are signifying no heart attack. And we want to see what are the main effective things to heart attack. So one of the things that you can see here, if you have family history, it's most likely that you will have heart attack. So that's something I can observe here. But most of the things are not that apparent. Specifically, so maybe for tobacco, yeah. For tobacco, using more tobacco consistently results in more heart attack. So these are the things you could see readily, but we are interested to summarize things mathematically. So let's look at the mathematical representation of what we see here. So we just run a logistic regression law on probability of heart attack on all the variables we have, SBP, tobacco, LDL, and so on and so forth. And here are the estimates we have. So let's look at the p-values we observe here. Here we have 30% p-value, so this variable is more likely nonsense. Same as this one, and that is interesting. Alcohol and obesity didn't get that much of a coefficient. That is perhaps because lower level of alcohols, latest studies have shown that results in less heart attack, but overindulgence in alcohol will result in more probability of propensity of heart attack. Some of the values that are very significant in family history here, lower density cholesterol and age. So for example, let's interpret family history. So let's see what this 0.93 means. So exponential of 0.93 negative 1 is equal to, so let me find it, exponential of 0.93 minus 1 is 1.53. So what it says is that if you have family history of heart attack, you're 153% more likely that you will have heart attack. And as you can see, the coefficient for age is also positive. That means more age would result in more probability of heart attack. Cholesterol has a very high effect on it. Tobacco also has significant effect, and I think if you just look at exponential of 0.079 negative 1, you roughly get 0.07, 0.08. That means if you're smoking, you're 8% more likely to suffer from heart attack in the future. And as you saw here, that's a very significant result. We could put everything together and you see that how we can interpret the results. Not only we can see the magnitude of what we have here, but also we can talk about the odds of heart attack in this case. So it's a very significant thing, and as we will see in our R sessions, in order to run a logistic regression line, you have to use a library called GLM. Another thing, and actually the last thing I want to explain now, is that usually in the studies that you're dealing with, you have unbalanced cases of treatment and control. For example, in the case of South Africa, I said 5% of people are suffering from heart attack, 95% are not. But in that data set, we had 160 cases of heart attack, 302 controls. That means 302 people didn't have, 160 people did. So in a sense, the ratio of heart attack, no heart attack was around 30%, 35% to 65% instead of 95% to 5%. When you have such unbalancedness in your data, you can easily fix everything by by just a simple distinction. One thing I want to point out is that, remember, in logistic regression we had intercept and some variables. I have a good news and bad news. The good news is beta 1, beta 2, and up to beta k will not, statistically will remain the same when you had a balanced or unbalanced data set or sample. So that was the good news. The bad news is beta 0 will change if you use the correct one. So for example, if you use a data set that has 35% heart attack rate in comparison to 5% of reality, the beta you get will be more than what you should have got. But you can easily adjust that beta by this transformation. So if you want to get the real beta hat, that would represent your data if the ratio of your cases and controls were exactly the same as the ratio of cases and controls in reality, would be the beta hat you estimate based on your unbalanced sample plus log here is again ln of pi, and pi here is the real proportion. So here in this case pi was 5% of 1 minus pi minus log of pi tilde, and pi tilde is the proportion you used. So proportion we used in this case was 0.35. If you just do that trick and replace beta hat 0 with beta hat 0 star, you will get the correct estimate of the probability that you're looking after. And then you can use it for predictions. So that's a very important thing. So if you have unbalanced things and you run your regression lines like this one, like the one that we had earlier, these coefficients will remain the same. What you have to do is to change the intercept, and the way you change it is by the adjustments we just explained. And you can show by simulation that no matter how unbalanced your data is, so let's say your control group should be 100 times more than your treatment group. So in the previous example, it was 5% toward 95, so the ratio was 19 to 1. But let's say it was 100. You can show that even in this case, if you run your sample with the ratio of 5 to 1, with the case ratio of 5 to 1, you're good. If you get it to 10 to 1, you almost do not improve anything more if you just have more balanced things. So if you stick to 10 to 1 or 5 to 1 ratio of your case and control, you're good. But make sure you do the adjustments after running a regression line. The last thing is using multinomial logistic regressions. When you have more than 2 classes, you can show that when you have more than 2 classes, you can easily make some adjustments to find the probability of each class, and just your prediction would be the class that has more probability to happen. It's slightly beyond the scope of our course. We are only considering 2 outcomes, but it's easily for those who are more interested in these topics, I highly suggest that you go over multinomial regressions and you still use GLM-net package, and you can easily assign probabilities there. You can show that this multinomial or just where you have k categories instead of 1 can be when k is equal to is equivalent to the cases that we explained earlier. So I stopped the course here, and we are going to continue on linear discriminant analysis and nonlinear discriminant analysis in our next lecture. Thank you very much. See you next time.